Okay, so are we there?
Yes.
44 in my computer.
10 seconds. You are already starting in YouTube, I think.
Mm-hmm.
Okay. We are live in YouTube now. You can start.
Okay, so are we there? Thank you very much. So it's a great pleasure to welcome here Nuno Araujo. So he is professor in Lisbon, and he will talk to us about self-folding Kirigami at the microscale. And I think best is that you have all the time, Nuno. Thank you so much for being here.
Thank you so much. Sorry, let me just switch on the timer. Okay, so good afternoon to everyone. First of all, I would like obviously to thank the organizers of the conference and the chairman for the introduction, for the invitation to be here today and to have the opportunity to talk about something that we have been working on over the last 2 years. And also for the effort to organize this conference, especially taking into account the current situation and the need to move online at a very short notice. So, as Herman said, my name is Nuno Araujo. I'm from the Center for Theoretical and Computational Physics at the University of Lisbon. And there, together with my collaborators, we have been developing theories and numerical models to study different aspects of the dynamics of soft matter systems. And among those systems are systems related to Kirigami. And so in Kirigami, the idea is to obtain 3D shell-like structures, like, for example, this soccer ball structure that I'm showing you here, from the folding of a two-dimensional template like this one that consists of rigid panels connected through flexible hinges. What is particularly challenging with Kirigami is to obtain the folded structure, the three-dimensional structure, spontaneously from the self-folding of the two-dimensional template. And so the mechanism that can drive this self-folding, it strongly depends on the length scale that we are looking at. And in particular here today, I will be talking about self-folding at the microscale. So when the size of the panels is of the order of the micron, and there, given the size of the panels, thermal fluctuations are important. So we can think about obtaining the folded structure from the random motion of the different panels. Well, this is an advantage, but it comes with a price. And the price is that due to thermal fluctuations, the trajectories of the different panels are stochastic in nature. So in many cases, instead of obtaining the targeted structure, what we get is some misfolded structure that is different from the target one. And so there are many open questions from the theoretical point of view about self-folding Kirigami, but today I will be discussing two of them that are related to optimization. In the first part, I will discuss how to optimize the folding in a way that we minimize the number of misfoldings. And in the second part, I will be talking about what sets the time scale for the complete folding of the structure and how can we minimize the folding time and how it depends on the geometrical properties of the net that we are looking at. So for that, let me start by talking about origami. That is probably a concept that you are more familiarized with. And this is a Japanese art where the idea is to start with a sheet of paper and then we fold it in a certain way in order to obtain a three-dimensional structure. And here I'm just showing you some examples of structures that resemble animals that were obtained by folding a sheet of paper. If now, besides folding, you are allowed to cut and to glue, this is what we call Kirigami, is also a Japanese art. And because of that, because you can now cut and glue, then you drastically increase the number of possible configurations that one can get, and therefore you have many more possibilities. And though you might not be familiarized with the concept of Kirigami, I'm pretty sure that at least as a kid you have played with something like this, where we start with a T-shaped two-dimensional template, and then if we fold it in the proper way, what we will get is a cube. But as I said in the beginning, we are interested in understanding how to obtain these structures spontaneously from the self-folding of the two-dimensional template. And as I said, it depends on the length scale that you are looking at. For example, if you think at the macro scale, when the size of the panels is of the order of the centimeter, then the interaction between the different panels is mainly an excluded volume interaction. We are talking about contact mechanics. And the mechanisms of self-folding are typically related to stress relaxation. So what we have is, and since thermal fluctuations are negligible at this scale, what we have is that the folding trajectories are unique, and we only have one folded state, and this is deterministic. However, if we go to the other side of the spectrum, if we look to the nanometer scale, and a good example is protein folding, then due to thermal fluctuations, what we will have is that the folding process is stochastic, but in this case, at this scale, the interaction between the different building blocks that here are either atoms or functional groups, then it becomes important, and this is what drives the folding, and it is believed that the folded state is the minimum of the free energy, so it's a unique state. In between, at the micro scale, what we have is that the interactions is such that we have also excluded volume interaction between the panels, but now due to thermal fluctuations, what we have is a random motion of the faces. And as you see, these faces, they have sticky edges. So when they come into contact, they bind in an irreversible way. And therefore, the final folded configuration is a kinetic structure that will depend on the kinetic pathways of folding. And so, as you'll see, this raises many interesting questions. But in particular, we can think about now using this strategy based on random motion to obtain these three-dimensional structures. And you can think about many applications like soft robots or encapsulation at the micro scale. But as I said, this comes with several different challenges. From the experimental point of view, one of the big challenges is to find ways to design materials that have an heterogeneous distribution of the stresses, in particular to be able to localize where the structure will fold. And here I'm just showing examples of possible ways to do that, like, for example, combining materials with different properties, like, for example, a material that is able to swell and a stiff material, or, for example, as here in the second case, using some material that is sensitive to light. So in the presence of light, it changes the mechanical properties and then it will fold in that particular place. Or using, for example, some droplet of a fluid that will shrink and will drag the different panels and make them close. But my focus today is on the theoretical challenges, and there you will see that there are many, many theoretical challenges. In particular, let's start with the simplest question. So take, for example, a polyhedron structure like the soccer ball that I showed you in the beginning. And now what we would like to know is what are the templates that we will call the nets that can fold into this polyhedron structure. And so one way to identify those nets is by doing a process that is named as edge unfolding, where the idea is that you start with a three-dimensional shape, and now you go along the edges, and you start cutting edges in such a way that you can now open the structure and find your template, so your net. And what you want at the end is that the faces that what was in the beginning, the faces of the polyhedron structure now become the panels of this template. And then you want to make them such that they have these flexible hinges between the panels. But the cut that you do to do the edge unfolding process cannot be an arbitrary cut. It needs to be done in such a way that it fulfills three different constraints. The first one is that the final net should be a single simply connected piece. You don't want to obtain two different pieces because this will increase the complexity of the problem, since in solution you will need to find ways to have these two pieces coming together and folding to form the three-dimensional shape. The second thing is that the unfolding, the net, should be the union of the polyhedron faces. So we can only cut along the edges, you cannot cut a face in the middle. The third one is that the unfolding should not overlap, because what we have in mind is that you produce, or you can cut this net out of a two-dimensional material, and for that it cannot overlap. And so the first question is, does every convex polyhedron have a net? And though there is no formal proof that the answer is yes, we believe that the answer is yes, just because up to now, nobody has managed to find a convex polyhedron structure for which there is no net. But this is still one of the open questions in the field. The second thing is, if you look even for the simplest case of a cube, and you look what are the possible edge unfolding processes or set of cuts that I can do to the cube in order to open to a net that fulfills the three criteria, what we see is that there are 11 non-isomorphic nets that can fold into the cube. I'm representing the 11 nets here. So there are 11 templates that I can start with and fold them in order to obtain the cube. And so the question is, from those, which one is the optimal one for self-folding? And so from the statistical mechanics point of view, we are looking to a problem of n to 1, where n is the number of nets and 1 is the folded structure that is the cube. So the problem is that imagine this, net that I'm showing you here. So if I now start to bind them according to the letters that I have at the side of the edges, so if I connect the A to the A, the B to the B, the C to the C, the D to the D, and the E to the E, what I get is a three-dimensional shape that resembles a boat. But if now I fold the structure in a different way, such that I now connect the A with the A, the B with the B, and so on, what I get instead is an octahedron structure. So for the same net, if I bind the edges in a different way, the faces in a different way, then I get a different structure. And what has been shown both experimentally by a group at Johns Hopkins University and with some direct numerical simulations by the group of Sharon Glotzer at the University of Michigan, is that the final folded configuration, it depends not only on the net that we start with, but also on the experimental conditions, in particular, the temperature, or if the temperature changes along the process. So what we are really looking at is to a problem of n to m, where n is the number of possible templates, the number of nets, and m is the number of possible folded configurations. The problem is that we have no clue what is the value of m. What are the possible structures that can be formed when we start with a given net? And this is also open question in the field. So one of the things that people have been trying to come up with simple design rules that would allow us to go through the list of all possible nets and choose the ones that be optimal for self-folding. In particular, when I mean by optimal here, I'm saying the ones that will minimize the number of misfoldings and will have more likelihood to form the desired three-dimensional structure. And so this is something that has been explored experimentally for the first time by Pandey et al. They did that in 2011 at the Johns Hopkins University. And what they did was to synthesize templates using rigid panels made of metal connected with solder. And they did it in solution. So in the beginning, the net was connected to a substrate, a silicon substrate, and then they heat up the system. And when they do that, first the template detaches from the substrate, and since the fluid is constantly put into motion, then they have a random motion of the different panels. And since they heat up the system, the solder has melts, and so the hinges become flexible and the structures start to fold. In addition, they coat the surface of the edges for all the panels with solder, and so when these edges become sticky, and so when two edges come into contact, they bind together due to the fact that they have solder there. And so what they did with this experimental system was to compare two different criteria for selecting the optimal templates for folding. The first one is a geometrical compactness argument, saying that from all possible templates, the one that will fold will have less likelihood of misfolding is the one with the lowest radius of gyration, the one that is more compact from the geometrical point of view. But the second argument is related to a to topological compactness. So what they did was to identify that we have different types of vertices in the template. In particular, we have a special type of vertices that are what we will call vertex connections, that are like this one, to which there is only a pair of faces that need to come together in order to close all the edges that connect to this vertex. If you think, for example, about this vertex here, in order to be fully closed around, one needs to close these two and then close these other two. So it's vertex connections are vertex that they only have one edge that needs to be closed in order to close all the edges around the vertex. And so they compare two different criteria. One is a topological compactness argument, saying that the best net is the one that maximizes the number of vertex connections. And the second one is saying that the best net is the one that minimizes the radius of gyration. And so in order to compare the two, what they did was to choose a certain number of three-dimensional structures. And for each one of them, they generate the full catalog of possible nets, possible templates. And for each, they choose 6. 3 related to the number of vertex connections and 3 related to the radius of gyration. And so what they did was, regarding the number of vertex connections, they took the one with the lowest number of vertex connections, intermediate number, and maximum number. And then the same for the radius of gyration. Lowest radius of gyration, intermediate value, largest value of the radius of gyration. And so for each of these nets, they perform 50 independent samples. And for each one of these independent samples, they follow the dynamics until it completely folds. And at the end, they classify the folded structure into 3 different categories. A means that is defect-free. It corresponds to the targeted structure. B meaning that there's only minor defects. It means that the faces are paired according to what was supposed to be based on the structure that you want to obtain, but the angles might differ slightly from what we would expect. And by slightly, they mean less than 20 degrees, what is already a quite large number. And C are all the other structures. They consider that they are defective, meaning that they have a significant amount of defects. So the better is the net that we take, the larger should be the fraction of configurations that are the fraction of samples that fall into the category A, defect-free. So here we have, for the dodecahedron, the comparison between the 3 nets based on the number of vertex connections and the 3 nets based on the radius of gyration. And you clearly see that the number of vertex connections, the topological compactness, is a much better argument and a much better criterion to choose optimal nets rather than looking to the radius of gyration. And they did it for different structures. You can see it here for the truncated octahedron, and you see precisely the same. The problem is that as they did, and based on their results, every time that you want to fold a certain structure, you need to produce the full catalog of nets. You need to count the number of vertex connections per net, and from those take the one that maximize the number of vertex connections. And this is possible to do to very small structures, but as you will see, the number of nets, number of possible templates to fold a 3-dimensional structure grows exponentially with the number of faces or the number of edges or the number of vertices. And so it becomes impractical to produce the full list of possible nets. And instead, what people have been doing is basically to generate configurations at random, and from those take the ones that maximize the number of vertex connections. But as you will see, this is very inefficient. And so what we did in 2018 was to show that it's possible to identify the nets that maximize the number of vertex connections in a deterministic way by mapping the problem into a problem of graphs. So what we do is that we define different graphs for this problem. The first one is the shell graph. So the shell graph is a graph where the nodes are the vertices of the polyhedron structure, and the links are between vertex that share an edge. So we have the nodes here and we have the links between the nodes. We can also define the face graph where the faces, the nodes are the faces, and we connect two nodes if they share an edge in the original 3D structure. So finding the possible cuts that I can do to my cube in this case is the same as finding a subgraph of the shell graph where the nodes are, so where the links are the edges that I cut in my edge unfolding process. And so since I want to open this structure, this subgraph that I will call the cut graph, and I'm representing it in red here, it needs to fulfill again three different criteria. The first one is that it should span all the vertices. Assuming that all vertices are in a place where the curvature is different from zero, this means that we'll need to have at least one cut in order to open the structure and make it that the curvature is zero there. So we need to visit all vertices. The second condition is that it needs to be loopless, because if you close a loop here in the cut graph, then you will be removing a face. So the cut needs to be loopless. And the third condition is that it should be a simply connected piece to guarantee that the structure opens to the same side. Because if it is disconnected, then one part will open in one side and the other will open in the other side. So in graph theory, if we want to look to the subgraph of any graph, in this case to the shell graph, that fulfills these three different criteria, then what you are looking for a spanning tree is a tree, loopless, that visits all vertices in the graph. And now, if we want to identify the optimal nets, so the spanning trees, the set of all spanning trees will be all possible nets, all possible templates that can fold into the three-dimensional shape. And now if we want to find the optimal ones, that are the ones that maximize the number of vertex connections, then what we need is to identify what is a vertex connection. And as I told you, the vertex connection is defined as a vertex that only has one edge that needs to be closed during the folding process. And so it means that in terms of a cut graph, is a node that only has one cut, only has one link connected to it. And in graph theory, this is what we call a leaf. So a leaf is a node with degree 1 with a single connection. So looking for the spanning tree that maximizes the number of leaves is looking for what is known as the maximum leaf spanning tree. And in fact, this is a classical problem in graph theory. There are many algorithms available that can allow us to identify what are the maximum leaf spanning trees of a graph. And so by doing this mapping, we can find the solution for the problem. We can, given a certain shell graph, we can identify what is the maximum leaf spanning tree in a deterministic way using this mapping that I have just shown to you. And this is particularly relevant because if you now look to what is the fraction of nets that are optimal nets, what is the fraction of templates that maximize the number of vertex connections, what we'll see is that this is in a log linear plot as a function of the number of edges in the shell graph. What we see is that it decays exponentially with the number of edges. So it means that, and these are the symbols are for different platonic solids, Archimedean solids and other solids. And the line is something that I will explain later, but this means that if we try to do the process at random, the likelihood that we'll identify the optimal net just by using a random exploration of the configuration space, it's decreasing exponentially with the number of edges. So for example, if you take a dodecahedron, it has 5 million spanning trees and only less than 2,000 are optimal. So if you do it at random, this means that in average, for each 2,500 configurations that you generate, you will find one that is optimal. So very inefficient. And this becomes even worse when you start to look to much more complicated structures. And the reason why it is, we can find arguments why it should decay exponentially. I will not go too much into details. I can give you a brief explanation of how we can get this solid line here. The idea is to calculate an upper bound for the number of nets. So you remember, we need to make cuts to the edges, and we need to make as many cuts as v minus 1, where v is the number of vertex in the polyhedron structure. So an upper bound for the number of possible cuts is saying that we need to look how many configurations I can have with v minus 1 edges out of the total number of edges in my solid. To estimate what is the maximum, what is the number of optimal nets, what we need is to calculate. So each one will have L leaves, and I don't know the number of L for the time being. Then it's how many configurations I can generate out of V vertices, knowing that L of them will be leaves. And so when you do that, and with some calculations, we can see that the number of leaves goes goes with the number of edges as e over 4, and the number of vertex goes e over 2. So when we put everything together, we see that the fraction of nets that are optimal decays exponentially according to this law. And as you can see from this plot, we explain quite well what we observed by counting all these configurations for all these solids. Another advantage of producing a full catalog of the optimal nets, now we are no longer producing the full catalog of possible nets, but rather of the optimal nets, the ones that have a certain number of single vertex connections, that are the maximum number of vertex connections. Once we have this full list, we can apply a second criterion. And for example, we did that for the radius of gyration, and we can show that if you first use as a criterion the maximum number of vertex connections and then the radius of gyration, you get a net that is very efficient in terms of percentage of successful cases that fold into the desired structure. And just to give you an idea of how good it is to have such a deterministic method, here I'm studying the case of the soccer ball. In the case of the soccer ball, there are about 500,000 optimal nets. But then if you look to isomorphisms in the graph, you realize that only 4,000 of them are different. But if now you rank them based on the radius of gyration, you clearly see that the radius of gyration initially increases with the rank. So if you are looking to the net that simultaneously maximizes the number of vertex connections and minimizes the radius of gyration, without such a method it will be impossible, because it's one out of many different configurations. We also perform numerical simulations, direct numerical simulations to follow the folding dynamics. And for that, what we do is to map our template into a set of nodes. So we represent each face of the template as a set of nodes. The blue nodes are on the vertices, and the red one is in the center of the face. And we model the interaction between these nodes in such a way that the interaction between the red nodes is a repulsive interaction. We use an exponentially decaying repulsive interaction, like a Yukawa type potential. And we model the interaction between the blue nodes as an inverted Gaussian potential, just to mimic the short range attraction between the edges of the different faces. So we performed simulations. And for example, in the case of the cube, we have analyzed the dynamics for the different nets. And with that, we can see, we can confirm what was observed experimentally, that the percentage of the percentage of cases that fold properly is strongly correlated with the number of vertex connections. And we can even rank now all the nets based on the efficiency of folding. But what is interesting is that if now we look into the problem and ask which one folds fast, what we see is that the rank is significantly different from the one we find for the minimization of defects or misfolded configurations. In fact, the one that folds fast is ranked fourth in the list based on the efficiency of folding. And so optimization really implies that we need to define for what criteria are we optimizing. If we are optimizing in terms of efficiency of folding or time it takes to fold. And so in order to understand what sets the folding time in self-folding Kirigami, what we did was to look to a very simple problem. So in order to avoid misfolding, what we did was to look into the folding of a pyramid, and this pyramid is on top of a substrate, so it can only fold to one of the sides, okay? And by doing that, there is only one folded configuration, so our number m that we didn't know is now equal to 1. There is only one folded configuration, that is the pyramid. And so we raise the question, how does the folding time depends on the number of faces that we have in this pyramid? And so we run numerical simulations using the strategy that I showed to you before. And what we observed is that the total folding time, the time it takes for all the faces to close, is a non-monotonic function of the number of faces. In fact, we see an optimal value around 5 that minimizes the folding time. And so in order to understand that, we started to make a statistical analysis of the motion of the different faces. So for that, what we did was to define an angle for each of the faces, here represented as theta I, that is the angle of the face with the substrate. And then we follow the time series of the angles. And what we get, in this case, for a pyramid with 3 lateral faces, so it has a base and 3 lateral faces, what we did was to follow the time series of these angles and look to the statistical properties of these angles. And before they close, the statistical properties of these angles, of the time series, resembles a Brownian motion in the space of the angles. So each face, what it's doing is a Brownian motion in space of theta. And what we notice is that when we look to this time series, we can see that the 3 faces are moving around due to thermal fluctuations in a random way, but eventually 2 of them meet at a specific angle that corresponds to the closing angle of the pyramid. And so when the 2 meet at a specific angle, then the 2 faces will close. So now, once the 2 faces are closed, the 2 remain in the same place, and the 3rd face, the only thing it needs to do is to diffuse until it touches these 2 faces, and then it closes. So what we see is that the first, what we see is that the first closing event corresponds to the time at which, for the first time, 2 faces meet at a specific angle, and the following closing events, they are just corresponding to the time it takes for the other faces, in this case, the final face, to close, to arrive to this angle where the other 2 are already closed. So from the statistical point of view, these are 2 different processes. So clearly the nature of the first closing event is different from what happens to the remaining sequence of closing events when we have more faces. And so we went to look into the statistical properties of the first and the remaining closing events and see if that could explain this non-monotonic behavior that we see for the total folding time. And so for that, what we did was to, if you now look to the first closing event for different number of faces, now what we can see is, so if we are looking for the time it takes for 2 faces to meet at a specific angle, then we could represent this problem in a 2-dimensional diagram, where in the horizontal axis, what we have is the value of the angle of one of the faces, and in the vertical axis, what we have is the angle of the other face, okay? And since each one of them is a constrained random walk, because it moves between 0 and pi, as we have a substrate, it cannot go to negative values of the angle. And so what we have now is we will assume that these two random processes are decorrelated, that there is no correlation between the two, so the two are independent. And so if the two are independent, if now we plot as a function of time the position of a point where the first coordinate is the angle of one face and the second coordinate is the angle of the other face, what we will have is a random walk in 2D, because the two coordinates are independent. And the fact that the two meet at a specific angle is a first passage process in time that corresponds to the time it takes for these two random walks to meet in this specific region of the configuration space. That is when the two have an angle that corresponds to the closing angle of the pyramid, okay? And so the first closing event corresponds to a 2D first passage process for a Brownian motion. So what we have is that is 2D because one dimension corresponds to the angle of one face and the other dimension corresponds to the angle of the other face. But now, as we increase the number of faces in our pyramid, we will increase the number of possible pairs that can be the first ones to close. So in fact, we will have n times n minus 1 over 2 possible pairs, okay, that can be the first ones to close. And so what we need to ask is, what is the typical time for the fastest of all these processes to occur? And this you can calculate, and what we'll see is that this time will scale with 1 over the logarithm of the number of pairs. If now you do the same, when you now look to the remaining closing events, so once this closing occurs, now all the other faces can connect to these two faces that are already closed. And for simplicity, we will assume that they can even close here at the top of the pyramid. And so if you do that, what you have now is a set of one-dimensional random walks that are basically the other faces, that they are moving around, but the first time they visit the closing angle, they will bind to the other faces that are already closed. And so the remaining closing events are 1D first passage processes. But now we will have n minus 2 possible of such process because all the other faces will need to eventually close. And so what sets the time it takes to fully fold our pyramid into the pyramid into the 3D shape is the slowest of all these processes. So now when we ask from all these random events that are first passage process, which one is the slowest of them, and we calculate what is the typical time, we see that the total folding time goes as the logarithmic of the n minus 2, where n minus 2 is the number of faces that still need to close. And so the total folding time is the sum of the first closing event, this T first, plus the time it takes from this first event to the point at which all the faces are already closed. So it's the sum of the two times. And so in order to check if this is enough to explain what we observed, what we did was to plot for different structures the folding time as a function of number of faces, and I will explain the data points later. So what we'll see is that the time it takes for the first folding decays with the number of faces, and the time it takes for the last one to close increases with the number of faces. And the sum of these two curves is the solid line that I'm representing here. And so really, we can explain the minimum value that is observed based on the sum of these two different times. So what sets the total folding time for a lower number of faces is the first closing event, is the bottleneck, is the one that takes longer, while for large number of faces, what sets the total folding time is the last closing, and that becomes slower and slower as we increase the number of phases. And is really this balance between the time it takes for the first closing and the last closing that sets the total folding time. What we did was, now that we understand what is the basic mechanisms that are affecting the folding time, is now to perform numerical simulations for different structures with different pyramids, with different closing angles, different number of faces, different temperatures that here are represented by different diffusion coefficients of the faces. And we can see that if we rescale time by theta star square, where theta star is the closing angle, and square because we are looking to a diffusive process, as a function of the number of faces. And if you properly scale based on diffusion coefficient, because diffusion coefficient is only also changing the time scale, what we see is that we have a data collapse of all the data points for the different structures, with the minimum always for values of the number of faces around 5. So it's clearly that what we are seeing is that the closing of these three-dimensional structures is driven by a diffusive-like behavior of the different faces, and that the closing events correspond to two different types of first passage processes in the space of the angles. So as a matter of conclusions, I would like to say that folding is an interesting problem from the statistical mechanics point of view, because it's really an end-to-end problem. And as I explained to you, we don't even have a clue of what is the value of possible folded configurations. That is significantly different from what people have been observing at other scales, like for example in protein folding, where the interaction is important, or at the macro scale where the trajectories are deterministic. That finding the net that maximizes the number of single vertex connections can be done in a deterministic way if we map the problem into a graph, because then this corresponds to finding the maximum leaf spanning tree of the shell graph. Also, that with that we can find the optimal solution in a unique way. We don't need to use random methods to identify what is the optimal solution. And that once we have the full list of, or the full catalog of optimal nets based on this criterion, then we are looking really to a tiny subset of the entire number of nets. And so we can apply other criteria to look for optimal nets based on likelihood of folding towards the desired three-dimensional structure. And really that looking to the optimal net in terms of reducing the number of misfoldings and looking to folding time are two different problems that need to be studied and understood in different, using different strategies, and that the folding time, even in the simplest case of a pyramid, is a non-monotonic function of the number of faces, and this can be explained by mapping the problem into Brownian, a set of Brownian motions, and identifying that the first closing event is a first passage process in 2D, while the second closing event is or the remaining closing events are first passage processes in 1D. So thank you very much for your time. Thank you again for giving me the opportunity to present this work, and I will be happy to answer your questions.
Yeah, so thank you so much. Thank you so much for this very clear and a very clear talk about this subject. So, which is really interesting. So I wonder if there are questions. You may put it on the chat or just ask for opening the microphone and your screen and your video. So there is a comment by David, very interesting talk. Maybe you have a question. Fabian Pauli has a question. Please go ahead. Maybe you can open your microphone.
Yeah, you can unmute yourself.
Fabian Pauli.
Let me see.
Or just place the question in the chat and then I will read it.
No, he's already unmuted, I think.
I can't, okay, I couldn't unmute, okay. So my question would be, I mean, I find this analysis with these graphs very interesting and seems to be super general. But then if you determine folding times, I think you made some numerical assumptions, right? So I thought that you have some attachment points where you have the interaction and so on. So how do folding times depend on your assumptions?
Okay. So what are our assumptions? The assumptions that we have is the interaction between the different panels are short range, okay? So, you know, in numerical simulations, if we want to do, even if we want to do some excluded volume interaction, we need to smooth out interactions. And so we did in a way that we have excluded, we have a short range repulsion between the center of the faces, and we have a short range attraction between the edges, okay? And so the assumption that we are using here, and this was the same for all the analytics and all SME analytics arguments that we used, was to consider that the two only stick together when they are at a very short distance, basically when they enter into contact, okay? And so what we have done was to study how does, for example, the total folding time depends on the width of the Gaussian potential. That will tell you what do you mean by short attraction, okay? And so what we have seen is that it might change the prefecture of the folding time, but does not change the relative order of the structures in terms of time that they take to fold, neither this non-monotonic behavior that I have shown you in the second part of my talk. Was that clear, Fabian?
Yeah, do you want to comment on that, Fabian?
I don't think so.
I think.
Can I talk again?
Yes, you can talk again. Yeah.
I somehow muted or unmuted myself. Sorry. Yeah. Okay. Thanks. But if you think about more like a soft system where you have a complete, let's say, interaction on the whole
edge.
Exactly. Would that change something now?
It will. So depends on the strength of that interaction. This is an important point, and thank you for raising that question. In fact, for example, imagine the case of Panday. What they do have there is that they have solder along the edges. So due to surface tension, you will imagine that when the two edges come together, that the solder, as soon as it starts to merge, will somehow drive the panels to meet and to close. So somehow this will work in favor of closing a bit faster than what is supposed to. And this is something that we have been looking at, is how does the fact that you have a drive for the closing will change some of these properties. But our understanding is that at least this general picture will still be valid there, but we might be changing the prefactors of the timescales.
Thank you.
Okay, thank you. Let's go for the next question. So this is by Oscar Leonardo. He says, very good presentation. Do you have any plans to go from theory to practice and fabricate the Kirigamis you are designing? Maybe you can also pop up, Oscar, and say something else, or just...
Yeah, you can use your video and mic. I unmuted you.
Thank you.
Oscar?
Olá, Nuno. Tens algum plano para ir de teoria à prática e fabricar essas estruturas?
Okay, yeah, okay. So we are obviously not planning to do any experiments, but we are talking with some people doing experiments and trying to validate experimentally some of our predictions. This is something that is in our agenda now.
Could you share what groups are you in?
Well, we've been talking with different people, but for example, I have shown here an experimental work by people at Johns Hopkins University, where they are doing this type of things already. But there are more groups looking into that. Yeah.
Okay, thank you very much.
Okay, thank you. And now there is a question by David. David, do you want to pop up? I see that you have your screen on.
So thank you for the very nice talk. Can you hear me?
Yeah,
Yes.
Yeah, go ahead.
Okay. So thank you. And so my question was, so you mentioned that it's different to the case of protein folding.
exactly.
And how, so like one question is like, how is it different? But also like, how do people study this with protein? Is it also through numerical simulation, or is there like experiment?
Well,
If you know these things, I don't know.
Yeah, so obviously I looked into that. So protein folding is a significantly different problem. It's in fact a very broad problem that has been studied for many years. In protein folding, what you have is that the interaction between the building blocks are important. Okay, so you have some electrostatic interactions between the atoms and things like that, and they play a role. And the question there is then why you get a folded structure, okay? And the typical assumption is saying, okay, the folded configuration is a minimum of free energy. So it's a unique state that corresponds to a minimum of the free energy. Different from that here, what we have is first, the interaction is excluded volume interaction, is just contact-like, okay? There is no long range or medium range interaction between the different components. The second thing is that every time you close one of these pairs of faces, then the time scale it takes to break is typically much larger than the folding time. And therefore, the process is irreversible. So the final folded configuration in our case is a non-equilibrium structure, is not an equilibrium structure. And therefore, the kinetics becomes even more important because the final folded configuration will definitely depend on the kinetic pathways of the folding. Does it make sense, David?
Yeah, it makes sense. But then if you, so just because in the protein folding problem, one of the problems is the misfolding. And in that sense, the misfolding is like secondary energy minima. Is it so? No, yeah.
Yeah, but there are some differences there. Obviously, you also get misfolding. And so some of the tools that were developed in that context, for example, to classify misfolding, identify different types of misfolding and things like that are important. Also, in the case of protein folding, we typically are looking to structures that are much larger than what we are seeing here in terms of number of units. And it's true that you can look to that. You need to be aware that the transition between the different configurations that are typically thermal activated processes, while here what we have is just diffusion of the different phases until two phases meet and they close. So it's a significantly different problem. We don't have activation barriers for moving from one configuration to the other. That's why we can look to this as first passage process, because as soon as they go to a certain region, to a certain angle, then they will close. You don't have a barrier, you don't need to have something that depends on temperature for a likelihood of accepting or not forming or changing from one structure to the other. Okay. Here, temperature is just rescaling time in most of the cases, though we need to be careful, especially if we look to some irreversible binding between these phases, then is a significantly different problem. And in that case, those type of arguments used in protein folding should be considered here as well.
Okay, thank you.
And then there is a question by Juan Shen. Please, maybe you can just place it yourself.
All right, thank you. Yeah, so thank you, Nuno, for your interesting talk. So my question is also on the experimental side. So do you know of any experimental materials that might be useful to study this kind of folding effect in your talk? And if not, then we might can do some artificial molecules. Then what is the criteria? So do they have to be microscopic at the nanoscale? And are there any other things to be taken care of?
Okay. Thank you very much for your question. So regarding the material, it strongly depends on how you want to do it. But for example, in the case of the work that I referred from 2011, they used some metallic material. In their case, the faces, they have a size of the order of 300 micron, what is not really microscale. So one of the challenges there is to be able to reduce the size of these faces. but in principle, this could be done. And especially now with the lithographic techniques, it's not so complicated. And I'm not an expert on experiments, so I should be careful when I say that it's not complicated, because it is. But it's technically possible to go to smaller sizes of the panels. I will be careful on using a strategy based on molecules, as you suggest, because then we are going to the nanoscale. And we have two problems there compared to what I'm looking here. First, you have the interactions, as I referred, and the second is that the faces will become flexible, okay? And here, I'm always assuming that the faces are rigid objects and they are not, it's not possible to bend them or to change their shape, because this is an additional degree of complexity into the problem.
Mm-hmm.
Thank you very much.
I see. Thank you.
Oh, okay, are there more questions, comments? Yeah, maybe if there are no, I mean, maybe I have a brief one. So essentially, if I understood well, I mean, the fact of having, so the faces do not unfold again, mostly because of the ratio, I mean, of the length of the places when they touch together, they touch over a long length, right? So the details of the potential are not that important, right? Okay.
That's also this, and the fact that, for example, at this scale, what we are looking at is things like solder and or other type of materials, for which the process of unfolding is a bit more complicated than just simply breaking a bond between.
I see.
Or electrostatic interaction that will be easier to.
I see. Okay. So I actually, in the experiments which you showed, there are always holes in their structures. Do you know why?
Well, I imagine that one of the reasons for that is if you don't do that, when the structures start to close, then you have a problem because you have a fluid inside and you have a fluid outside, and then the interaction of the fluid becomes really important and very likely very difficult to close the structure, right?
I see. Okay. And I wonder, I mean, related to the last questions, of course, when you have a crystal, so indeed, if you are in the situation like, for example, the allotropes of graphite, carbon, you know, so you have graphite, graphene, and carbon nanotubes. So then I understand that this is a difficult situation. However, there is a sort in crystals, there is a sort of intermediate situation where you can have rather big chunks of crystals whose directions of whose shape is essentially determined by the crystal symmetry. And maybe that could be considered to try to start with something which is relatively flat, but relatively big, to cut it in the proper direction and see if it folds. Did maybe anyone think of that, or is it kind of too?
Well, a lot
crazy?
of people are now looking to Kirigami with graphene. And in particular, if now you use graphene to produce these faces, provided that is structure with a couple of microns, then the fine details that you are saying, that is a classical thing with graphene, of how you cut, and this will give you different crystal orientations along the interface. This will be relevant because this is in the scale of the angstrom, and now you are looking at the micrometer scale. So yeah, it could be a way of producing these faces, and most of these things in principle will be valid, provided that you are with faces that now have a scale of the micrometer and no longer just a couple of nanometers, okay? And also, yeah, and the advantage of that, you can also coat the surface with some kind of molecules that will lead to, or will fine-tune the interaction between the different panels.
But I mean, could you predict, for example, for a triangular symmetry of the crystal, which would be the best cut to obtain a certain structure? If this crystal is square, you may need another cut.
Yeah, this is a different geometrical problem. Yeah, in principle, it can be done. But what I'm saying is that for the type of folding that I'm looking here, all these details at the atomic scale will be relevant for. But in principle, yes, once you have the structure, and this is something that people have been looking at. So people that do Kirigami with the graphene, this is the type of things that they are looking at, is what is the proper way to cut such that you really minimize the number of degrees of freedom that you need to control in order to change the shape from one configuration to the other. Right? Ideally, you only want to change 1 degree of freedom, and with that control the full structure.
Okay, thank you very much. Are there more questions or comments? So if not, maybe we can make a photo, Ramon.
Yeah, you can all turn your cameras on. You are allowed to do it now. And you just take screenshots in your computers.
We'll take 1, 2.
Let's take a few of them, yeah. Maybe another one because not everybody has their cameras on.
Bueno.
Okay.
So hope next time we can see each other on a coffee break.
Yes. Thank you very much. Yeah.
Thank you so much. Thanks. Yeah. Thank you.